Hey everyone, I'm Anish and welcome to PrepFusion. So this is the lecture 17 of the state space chapter. So in previous lecture, like I stopped in between. I thought like I will cover these two topics as well, but the lecture was going very long. Okay, and if I start this topic, right, I have to complete this one. Okay, so the previous lecture, right, I started like with the concept of observability in practical approach, and I like explained it to you like in practically why the concept of observability came, right. Then I proved like how you take the state feedback and how you observe the state variables and you estimate the state variables, right. And then we proved that the error was going to 0 if the eigenvalue is negative, right, if I get the negative eigenvalue. Okay, but here then I proved the Kalman's test for observability. I was starting with the proof and we went along. Okay, and here we got that rank of this one should be non-zero. So one more thing, this proof is not that important. Okay, so if you don't understand this proof, right, that's totally fine. Okay, you can skip this part. Okay, not that important, because in gate, right, you have to just solve the question. Okay, that is important. Proof is not. Okay, everyone in any else coaching, right, any other coaching, they don't even do the proof. Okay, directly go to the equation. Okay, so don't worry. Okay, you don't have to understand the proof, but just to like give you an intuition like where this matrix came from. Okay, that's why I wrote the proof, right, did the proof. Okay, else it's not important. So I will say proof is not important. So here I should write proof is not important, right. Proof is not important. Okay, just the final conclusion is important, just so that you can remember this, right, forever. That's why sometimes I do the proofs. Okay, so yeah, we understood that for my system to be not controllable. Okay, I again here made a mistake. It should be observable, right. It should be observable. Sorry, observable. Okay, so for my system to be observable, this matrix should be full rank matrix, right. This matrix should be full rank. So even if I mess up some controllable observable, just forgive me. Okay, because there may have been like with the flow I am going. Okay, so maybe instead of writing observable, I wrote like observable, controllable, then some mistakes may happen. Okay, just just now I checked the notes and there was a mistake. Okay. So yeah, now let's do the Kalman's test for observability. Okay, again, like here I have also written wrong. This is observability, sorry, observability. Okay, so like we've already proved it. This is the basically the observability matrix, right. Now yeah, as I told, right, if you take the transpose of that one, we get this one, right, in row format, just because writing this is easier in single line than that one. Or there is one another matrix. If I do QO whole transpose, this also you can solve, and we'll solve like this also, and like this one, like answer from both should come same. Okay, but like solving through this one, right, you don't have to again do the transpose. That extra step is getting reduced. So like if you're confident enough, you can do it like this one. So we will solve with both ways, then you will understand. This will become CA, then this will keep on going on and up until CA n minus 1 it will end, right. It will be n cross n. Okay, so yeah, this is basically it. Now this, right, like whenever you're confused or something, always use this formula. Okay, the next method is Gilbert's test, but if you're confused, don't worry, just use this one with your eyes closed and you will get your answer. Okay, so whenever you get confused, use this one. Okay, so now what are the cases, right. So I told you that for the system to be observable, this observability matrix has to be a full rank matrix. So case 1, if the observability matrix mod of q0 is not equals to 0, then our system will be observable, right. What does this represent? Basically mod of determinant of q0 not equal to 0. This represent that q0 is a non-singular matrix, right. It is n cross n, and hence it is a non-singular matrix, right. It is a non-singular matrix. So what will be the rank of this observability matrix? If my determinant is not 0, it is the full rank, right. n, right? N. So now I will go backwards. So if my rank of the observability matrix is n, right? If it is equals to n, okay, I should write this as equals. Then what I can convey from this implies that my system is observable, or my state space representation is observable, right? This implies is observable. Okay, always will be given the state space representation, right? So this is the basic meaning. Now I will again copy this like case only. So the difference will be that in case 2, right, my determinant will be 0 for the controllability matrix and things will change a bit, okay, but the basic concept is same. So case 2, what is happening? Case 2, the determinant is 0, okay. Basically the determinant of the observability matrix is equal to 0, hence this q0 now becomes a singular matrix instead of a non-singular matrix, and rank is less than n, right? Rank becomes less than n, okay, because like full rank matrix will have determinant 0, but anything less than n will have determinant 0. Full rank matrix will have determinant non-zero, and anything less than n for the rank will be determinant equals to 0, okay, always. So if my rank, now vice versa, what I can say in reverse direction, if my rank is less than n with the observability matrix, then my state space representation won't be observable. So here instead of is observable, I can write here won't be, okay, won't be observable, right? So yeah, this is basically my rank basically. So now, right, what does this observability matrix states? So I should write this as q0 and also q0 comma observability matrix, okay, or okay, q0 I should write in bracket and first write observability matrix, observability matrix defines the relationship, okay, wait, between the output and the input, right, of the state variables, right? Between the output and the state variables, basically defines the relationship between outputs and the state variables. So I can put this state over here and variables over here, okay. So yeah, this is what my basically observability matrix defines, right? So yeah, this was the Kalman's test, very short, right? Whenever you're in doubt, just use there will be two cases, right? One case where the determinant is not equal to 0, then it will be observable, and another case is determinant equals to 0. Basically the observability matrix determinant is equal to 0, okay. So observability matrix, how you will find, either like this one or this one, just the transpose of these two, okay. Just we have to take care of the determinant, right? So determinant doesn't change even if we take the transpose. From there also you can understand that determinant doesn't change even if we take transpose. Determinant of A transpose and determinant of A will be same like rank of A and rank of A transpose will be same for a square matrix, okay. So it is important to keep those things in mind. Now let's start with the Gilbert's test, right? Now first what I do, again follow the same procedure as I followed like the previous case, right, in controllability. So Gilbert's test for non-repeated eigenvalues, simply like a diagonal matrix, okay, non-repeated So using this test, just by seeing the A matrix and the C matrix, because this time the output, right, is related like related with the C matrix and the A matrix. So but just by observing the C and A matrix, you will be able to tell whether the state space representation is observable or not observable, right? So I will write that same thing also, like as this time my y of t is a function of both C and e raised to power at, okay. So my observability will depend on C and A, okay. we don't need to get any information about the B matrix, because anyways we make the input as 0, right? Like for that Kalman's test. So what is my A matrix? This is lambda 1, lambda 1 0 0, this is 0, lambda 2 0, this is 0 0, lambda 3. Okay, so this is basically let's say my A matrix, which is a diagonal matrix and with non-repeated eigenvalues. So lambda 1 is not equal to lambda 2, is not equal to lambda 3. And what is my C matrix? C matrix is like this one. Let's say this is my first element C11. Okay, let me say this C1, C2 and C3, right? So only one row, basically one output, right? So what is the thing that we need to check, right? So what does my y of t become? So y of t is something like this one, right? Y of t is something like this one. So I will break this down, okay, into simple equation format. So what will be my e raised to power at? So my e raised to power at, right, it will simply become e raised to power lambda 1t e raised to power lambda 2t. I will not prove it, okay. I think I have proven this one already, or if I haven't, I don't remember. I have already proven it, so I will prove it again. So this is 0. If I take the exponential, right, this becomes 0, this becomes 0 0, and this is the matrix, right? So yeah, so what is my y of t here? Y of t will be c into e raised to power at into x of 0. Sorry, I forgot to wrote here the x of 0 basically. So this will be my x of 0, sorry. Okay, so sometimes we also tend to forget things. So here my y of t will be c into e raised to power at into x of 0, right? So if it is c into e raised to power at into x of 0, then I know my c, I know my e raised to power at, and x of 0 is x1 0, x2 0 and x3 0, right? Because the order is 3 cross 3 matrix, right? 3 eigenvalues. So yeah, let me write this in smaller pen because we won't be able to fit in everything. So first I will copy the c, this one I will copy, okay. And this one I will copy, okay. And this is into x1 x2 x3 0, right? So into x1 0, x3 0, and so not x3, x2 0 and x3 0, right? So this one, what does this become? So simply, right, it becomes again a 1 cross 3. So this, and this is 3 cross 3, this will again become a row matrix. This will be c1 times this and this times this, so this becomes 0. So only we are left with c1 times e raised to power lambda 1 t, and this will be c2 into e raised to power lambda 2 t, and this one will be c3 into e raised to power lambda 3 t, right? And at the other end, what do we have? We have x1 0, x2 0 and x3 0, okay. So this is what we have. So now just simply convert it, right? So how to convert this? So simply, right, what I can write now, I will write in thickness. So this will become c1, this is just a scalar, right? So this is e raised to power lambda 1 t into x1 of 0 plus c2 into e raised to power lambda 2 t into x2 of 0 plus c3 into e raised to power lambda e raised to power lambda 3 t into x3 of 0, right? So this is my basically c1 c2 c3. Now what we can understand, simply from this equation also we can understand that if my c1 becomes 0, then I will have no information about the state variable, okay. I won't be able to observe, this is the output that I am taking, my output won't be able to observe anything, right, about the first state variable. So c1 can't be 0. Now if c2 is 0, then I won't be able to get any information about the second state variable, and similarly for c3 also. So this is, from here we can understand also the that I told you in the first lecture, like the previous lecture, that like what is basically the meaning of observability. getting the information about x1, x2 and x3. But can we change the states? We can't change the states here, but with the help of controllability we could have changed the states. But here we can only observe the states, that what is my x1, what is my x2 and what is my x3. All these things we can observe, but we aren't able to change the states. Okay, so that is the important point to note about observability and controllability, right? From here also we can understand. So what is the point that I wanted to write here? So what does Gilbert say? So Gilbert basically says like if one of the elements of the row is 0. So like what I wanted to mean here is, so let's say we have two outputs, right? So this will be like C12, C13, C13. So at least one element should be non-zero in each column corresponding to the each column of the A matrix. So okay, I should write this, at least. I will then explain it. At least one element of C matrix should be non-zero. Okay, one element of C matrix should be non-zero for like system to be observable for state space representation station to be observable. But what is this condition for? This is for non-repeated eigenvalues, and the system matrix is diagonal matrix. So A is a diagonal matrix, right? So for this case only this rule is applicable, right? So yeah, like why am I saying that at least one element of each column should be non-zero? So let me take another example. So what example I will take this time is, so I will take this one as let's say this is C12, C13 and C10. So this is C11 and this is C22, C22, not 22, C21, C22 and C23. Okay, so I have two outputs this time instead of one output. Okay, then what will happen? So here, right, instead of this matrix I will change it to this matrix, right, this one. And this time I will do a bit different thing. Reduce the size. What I will do is, instead of multiplying with this lambda t, oh, I can do this also. So what will happen? So this one will change to simply, okay, let me make a bit of space then. This one will come here, 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 this one will come here. Okay, so this is C11. Okay, this is C21, C31, sorry, not 31. Okay, I made a mistake. So this is basically C11, C12 and C13, right? And yeah, this one will be compressed here, and I can get this to here, bring this to here, and the same thing, right, will be copied in the bottom also, just with different namings, right? So how I'm doing this is C12 times this one. Okay, this is how this is C12. I wrote this C12 again. Okay, too much of stuff happening. This will be C11, right? So yeah, C11, C12, C13, C21, C22. Yeah, so this is C11 again, right? C11 again. So C11 times e raised to power lambda 1t. So this becomes this one. C12 times this 0 and 0. So this becomes 0 only. Okay, but then what I do again, I go to the next column, right? So C12 times C11 times this one 0, C12 times this one e raised to power lambda 2t. So I get this one. So first row is like this one only. Okay, then the second row will be the same thing, okay, just the this time the second row will be multiplied, right? So this one will be this is simply C21, C22 and C23. So C21, C22 and C23, right? So this is this one, okay. So yeah, this is how this is. Now this is a basically 2 cross 3 matrix, and this is a 3 cross 1 matrix. So what I will get? I will get a 2 cross 1 matrix, right? So okay, I don't, okay, 2 cross 1 matrix, how I will get? So this one, my y of t, I have 2 outputs, right? 2 outputs this time. So my y of t, the first one will be like this one only, right? Okay, I should generally I have 1 output only, but I'm doing it for 2 outputs just to show you. My y of t equals to c11 e raised to power lambda 1 t. So this is c11, this is c21, or not c21 actually. Let me write this in bigger pen. Okay, this is also, let me make this smaller actually. C11, then C12, and then C13, right? And like we have 2 outputs, right? 2 outputs. So with either one of those outputs, I can at least get, right, if even if one of them is non-zero. So now this one will be simply copy paste of this one, okay, but the namings will change. So this one will be like this one, but the names, the suffix will be 2's this time instead of 1's. So this one will be basically 21 and 22 and 23, okay. So yeah, so what I can observe here is, even though let's say my C11 is 0, C1 is 0, but I can get information about this first state variable using the second output, okay, with the help of C21. So at least one of them should be non-zero, right? If one of them is non-zero, then I will be able to receive the information about the state variable of that particular state, right? First state variable. Even if like if this is 0 but this is non-zero, then I can. But if both of them are 0, then this second state variable is totally gone, right? Second state variable is totally gone. Like with the first output I can't observe, with the second output also I can't get the information about the second state variable, okay. That is what I told, right? At least one element of C matrix of each row, sorry, of C matrix of each row of C matrix, each row, okay. How do I, C matrix should be non-zero, okay, should be non-zero for state space representation to be observable, okay. So yeah, that is the one thing, okay. But this is only valid, okay, I should write this as only valid when my matrix A matrix is diagonal, right? Only valid for non-repeated eigenvalues and A is diagonal matrix, okay. So yeah, with the single output also I explained, and with the 2 outputs I explained, like why only one element can be like at least has to be non-zero, okay. So each, sorry, not each row, actually each column, sorry, each column again, right? Some mistake would have occurred. So each column, this is, let's take this off through here, right? At least one element of each column, right? Each column has to be non-zero, okay. Then my system will be observable. So this is very important point, okay. So yeah, this was the Gilbert's test for the non-repeated eigenvalues, and now let's do the Gilbert's test for the repeated eigenvalues. So I have already written it down here. So for repeated eigenvalues, what is this? Repeated eigenvalues. So this time, right, I won't prove it. Okay, you just have to remember this. Okay, so if the eigenvalues come as repeated, you can either do the Kalman's test or you remember the rules. I will not prove it here this time, right? So because the lecture will go again long. So here, right, my lambda 1 is repeated, and this is Jordan matrix. Okay, this is Jordan matrix. So if there is one above, so this is a Jordan block and this is another Jordan block, and I have, let's say I have a C matrix here. Okay, so what are the rules for repeated eigenvalue for the state space representation to be observable? I've already written it down. For same eigenvalue, there is like too much hectic here. Okay, there should not be more than one. Okay, one Jordan block, basically I meant to say here Jordan block, one Jordan block. Again the same rule as the previous one, right? So for the same eigenvalue, there should not be more than one Jordan block. In this case, how many Jordan blocks we have? We have two, not one. Okay, I didn't ask for the same eigenvalue how many Jordan blocks we have. I asked just simply how many Jordan blocks we have. We have two, right? But for the same eigenvalue, how many Jordan blocks do I have? We did a question on Jordan blocks, right, in the controllability lectures. So for the same eigenvalue, this is the same eigenvalue, only one Jordan block, right? So because we go like diagonally and above this is 1, so this will be included in the Jordan block. Okay, so yeah, we have already done this, right? I won't explain it further. So only one Jordan block, so this is okay. Okay, this is okay. So first rule is satisfied. Okay, second rule, the first column corresponding to each Jordan block of C matrix should be non-zero. Okay, so here, right, the first column corresponds to each Jordan block. So this is Jordan block, so this column, right, should be non-zero basically. Okay, non-zero. Now if there are two outputs, I don't remember exactly, but I think at least one of them should be non-zero. I think that was the rule. So let's do it for single output only. So if it is a single output, okay, then what happens is, this is Jordan block, right? This is Jordan block and this is another Jordan block. So what is the first column corresponding to the Jordan block? This time I won't be taking the information about this one. I am more interested in this column, right? This column. So I go to this column and I find that corresponding to this column, my C matrix is the first element, right? In the C matrix, the first element. So this element should be non-zero for my state space representation to be observable. So what does this say? The first column corresponding to each Jordan block, so each Jordan block, first column corresponding to each Jordan block of C matrix should be non-zero. So this should be non-zero. Okay, so C1, according to this condition, C11 has to be not equal to 0, and I can't have more than one Jordan block. Then like this doesn't have any more than Jordan block, so C11 shouldn't be equal to 0. Then this system will be observable. Is that enough condition? No. Like this lambda 2, right? This is also another Jordan block, right? So another column corresponding to this Jordan block, this is only the one element only, and this is the first column only. So this C13 column corresponding to this Jordan block of C matrix should also be non-zero. Okay, this C13 should also be non-zero. Then like two conditions I have to satisfy. C11 has to be non-zero and C13 also has to be non-zero. Then this state space representation will be basically observable, right? Will be observable. Okay, so yeah, if we don't like this is too hectic, or you might seem this is my duty to tell you all the rules. Okay, my duty is to tell you all the rules, but if you are feeling overwhelmed, okay, then what you can do, you don't solve for repeated eigenvalues using Gilbert's test. Only use the Gilbert's test for non-repeated eigenvalues. That is very simple. Okay, very simple. And then use the Kalman's test for anything else, because Kalman's test is universal. Okay, this is universal. This test is universal, will always work no matter what. This test will always work. There is no exceptions in this as rules as such. Okay, so yeah, this is basically my Gilbert's test theory basically. Now, right, let's solve few example questions on this one. So here, right, check for controllability and observability for the state space representation. So if we had Kalman's test, right, what we would have done? We would have basically multiplied the matrices and then solve for it. but as I can see, this is a diagonal matrix, okay, but this is a repeated one, right? So this is following the second Gilbert's test, that is the Gilbert's test for repeated eigenvalues, okay. So first check for controllability. I hope you remember, right? I hope you remember that what was the controllability thing. So like for controllability and observability, what was the first condition for Gilbert's test? Basically, I should not have more than one Jordan block for repeated eigenvalues, for same eigenvalues, okay. Here what I see, how many Jordan blocks we have? Okay, we have 3, right? 3 Jordan blocks. This is 1 and this is also 1, because here we don't have a 1 here. So this will be 1 Jordan block, this will be 1 Jordan block, and this is also another Jordan block. So corresponding to the same eigenvalues, we have 2 Jordan blocks, right? Hence at starting itself, without even solving anything, okay, I can say that this is a unobservable and uncontrollable state space representation, right? Hence I will answer unobservable and uncontrollable in just 2 seconds, okay, in just 2 seconds. But if you solve it using Kalman, you will see that yeah, this is coming unobservable and uncontrollable. You find the determinant of those 2 blocks, right? So what is the homework for you? So as I don't want to make this lecture very long, so homework for you is to calculate using, so this is the method 1. Method 1 is using Kalman's test, okay. So this is the homework for you, not for me, okay, because this is a simple calculation, simple matrix multiplication, and then finding the determinant that you can do, right? So this is what you have to do, and cross verify whether the system is coming unobservable and uncontrollable as I solved it using the Gilbert's test. So method 2 is Gilbert's test, right? So okay, let me write this a bit better manner. So for Gilbert's test, right, for Gilbert's test, basically I will just take the A matrix, okay, because the first rule isn't even satisfying for both of them, right? Because if first rule doesn't satisfy for one of them, the rule is same for both of them, so it won't satisfy for the other one also, okay. I am talking about the controllability and observability. So again, what do I see? I have 1, then 2, right, and then 3, right? Let me do this in another pen. 3. So I have 3 Jordan blocks is fine, okay, 3 Jordan blocks is fine, but the issue is what? For -1 I have 2 Jordan blocks, right? For okay, let me say lambda 1 equals to -1, I have more than 1 Jordan block, okay. Jordan block, then my state space representation will be uncontrollable and unobservable, okay. Okay, let's go to the next question. So in the next question, we have to check for state controllability and observability of the system for the state space representation. So the question will come like this, right? So the question will tell you to find the controllability and observability, both of them at once, okay. So from matrix itself, can I say something? This is a diagonal matrix, right? So I can use that Gilbert's test for the non-repeated eigenvalues, because my eigenvalues are not same. So my row corresponding to this is 1 non-zero, and row corresponding to this is non-zero. Again, column corresponding to this is non-zero, and column corresponding to this one is 0. So it is what? It is controllable, but it is not observable. Now what is your homework? Your homework is you have to solve this using Kalman. So again, right, So this is your homework, because I don't want to make the lecture lengthy. So Kalman's you can do. Okay, Kalman's you can do. It's simple formula, right? Simple formula. So you do it like both. Okay, first that AC one, and then this what do you call? So you do it, solve for QO, and you solve for QO transfers also, and then also check that are the ranks coming same. Okay, so from there you will clear your concept. Yes, the ranks are coming same, right? So like this has two methods. Method one is using Kalman's test. This is homework for you. So you have to do few things by yourself now. Okay, I won't do everything now, so because else you will not learn anything, right? You will just see what I am teaching. Okay, that is not good. So you have to solve questions also. So method 2, what is method 2? Method 2 is basically Gilbert's, right? Gilbert's test. So if I can see the Gilbert's test, right? If I can see the Gilbert's test, what do you see? So I will copy all these things. Okay. Okay, ABC. Okay, so now what I can see, like this, I told you, right? This is non-zero, this is non-zero, and this is non-zero, this is non-zero. So like B, all the elements are non-zero, hence controllable. So right, controllable, and this is not observable. As where did it go? One element is 0, and here all elements are non-zero. So what does happen? So this one, right? So can I now draw this, and from there you can understand that why is this happening. So these are my ABC matrix, right? ABC matrix. Okay, so I can convert this in like these are in diagonal, right? Parallel. So I can convert each of them. So the first one is just one integrator, and I have -1 in feedback, right? So this thing like is in a grip right now. Okay, just in a grip, solving each of them. Okay, in like deducing them into state diagram. So this one should be in a grip. So I will solve this directly now. So I will write this. So I will have two paths, right? Two parallel paths. So one will be this one, another will be this one, and one has a feedback. Both of them will have integrators, right? One by s and one by s, and both of them has feedback of what? Feedback of -1. -1, right? And this one has feedback of -2. Now what is the difference this time? This first one, right? First one is connected, first state variable. This one is x1, so I should write this one as x1. Okay, and this one as x2. So this first state variable is connected with the output, but the second isn't. Okay, that's what I was telling, right, in the derivation part of the Gilbert's test, right? So this first one is connected with the output, but this second one isn't, right? This is one only, second one isn't, because here the gain is 0. So this is disconnected. So this, okay, this is -2, and this is 1. This is the first one is 1, this is -1. Okay, so yeah, this is my u basically, and this is my state diagram, right? So from here also I can understand what is happening here. What is happening? There is a pole 0 cancellation. Basically there is a pole 0 cancellation. Due to that one, the system is will either become observable or unobservable or uncontrollable. So here, right, due to this breakage, there is a pole 0 cancellation. Okay, so either my system will become observable or unobservable or uncontrollable. Okay, so right, what is my transformation basically? From here, can you tell me the transformation? So transfer function is basically this 1 by s divided by 1 by s times this both of these statements. So yeah, let me solve this first. So, or you can simply add them, right? So due to this one I will apply simply superposition. Okay, due to this one is 0 only, right? Due to this one, what is this? 1 by s plus 1. So it is 1 by s plus 1 plus 0 by s plus 2, right? So this is my y of s over u of s. So it is becoming 1 by s plus 1 only, right? 1 by s plus 1. Okay, so this is my transfer function basically. So like if you want to solve using SFG, then there you will see that there is a pole zero cancellation. Let's solve using SFG. So this was using superposition. Here I am not able to see, but if I multiply a pole 0, s plus 2 and s plus 2, why am I multiplying, dividing? Because I have two integrators, right? I have to make it order 2 because system is order 2. I mean the state space representation is order 2, so I have to get second order in the characteristic equation in the denominator, right? That's why. But in actuality I can represent this only with one state variable, but it has overcompensated using two state variables. That's why either it will be uncontrollable or unobservable. Okay, so that is the reason. So yeah, from here you can understand, or from what you can do is use Mason's gain formula. So there you will see there is a direct pole zero cancellation. So what is the Mason's gain formula? So Mason's gain formula, right? This is the first one. So it is 1 times 1 by s times 1. So the first path is this one only. So I have 1 by s into 1. I have this loop, right? This loop I have, right? So like this is isolated from this one, this forward path. So this is minus 2 by s. So this becomes 1 minus 2 by s, and two non-touching isolating loops. No, I don't have, right? And what is the delta? Delta is basically this loop and this loop, right? And they are non-touching also. Okay, so 1 minus 2 by s, this is the like bottom loop, and the above loop is minus 1 by s, then plus minus 2 by s times minus 1 by s, right? Is minus 1 by s times minus 2 by s, and then again I will add these two, so this will come over here. Okay, so what do I get? So this becomes this becomes 1 by s and 1 plus 2 by s, and in the denominator what do I get? I get 1 plus 3 by s plus 2 by s square, I think. Yeah, this one, right? Yeah. Now multiply s square both numerator and denominator, then what do we get? We get s into s plus 2 divided by s square plus 3s plus 2. Now can we take anything in common? We can, right? We can take anything in common. This is s. Okay, what is wrong? Okay, this is not s actually, this is 1 only. Okay, because 1 by s times s is 1 only, right? So this is 1, and this is s plus 2. Now what is this? Factorized to s plus 2 plus s plus 1, right? So here I can directly see there is a pole zero cancellation. Okay, so it becomes ordered 1. So from here also you can understand there is a pole zero cancellation, right? So from here also you can understand that the system will be either controllable or uncontrollable or unobservable, right? Pole zero cancellation, right? Okay, so this was the 40th question basically. So again, right, check for state controllability and observability of the system for the state space representation. Now tell me, for this transfer function, will it be controllable or uncontrollable, observable or uncontrollable, unobservable? So pause the video and solve, right? Okay, and think for this question and tell me. Okay, so here now have you thought about it? So if we said that it is uncontrollable, okay, uncontrollable, okay, then you are wrong. Why? Let's see. for pole 0, right, there is a pole 0 cancellation, right? So you might think there is a pole 0 cancellation, so it can be uncontrollable. Now if you would have said that this is unobservable, then also you are wrong, right? Now if you would have said that it is both uncontrollable and unobservable, both, let me copy both of these two. Okay, let me place this one here and let me place this one here. Then also you are again right, again wrong, right? Again wrong. Why? Because the thing is, it can be any three of these, right? Any three of these. So if there would have been an MSQ, right? MSQ, so you would have ticked any three of this. So any three of this would be the answer, right? It can be uncontrollable, it can be unobservable, or it can be both uncontrollable and unobservable, right? So we can't say without knowing the state space representation. So here, right, if MSQ has come, so you will mark these three or whatever options are present out of these three, you will mark those, okay? But if a simply like just a MCQ has come, right? So if nothing is given and MCQ has come and you have to answer one of them, so you mark both uncontrollable and unobservable, because you don't know, right? Why you don't know, I will explain it to you. So what point I should write? We can't say as state space representation is not given. Okay, we can't say as the state space representation is not given. So how many types of representation that does this can have? So this is right, this is one of the representation that I'm drawing. Okay, I will just, what I will do, I will just copy the previous one, because it's like the previous one only, right? Previous one only. Okay, this one. Okay, so this right, I had the state space representation this time. Like this 0 meant something here. Okay, this 0 meant that I will have not link. Okay, but instead of 0 here, if I had a 0 over here also, 0 over here also, then also my transfer function would have remained same. Okay, transfer function would have remained same, and this link would have been broken. Okay, but this link would have stayed, right? But my transfer function would have remained same. Okay, so yeah, that is the main thing. So transfer function is unique, but state space representation isn't, right? So this is the whole motto of this chapter. So I've copied this one, so I will take this one. So my state space representation, right, this one is one of the state space representation. Okay, and I can have another also. So how? What I will do, simply I will break, I will connect this line. Okay, connect this line, but break this one. Break this one, right? So if I break this one, what do I get? What do I get? So basically, right, this again I will get the same transfer function. Okay, you calculate, you get the same transfer function, right? So this is also another way to do, right? Another way to do. So what is another way? So another way is basically you break both of them, right? Then also you will get the same transfer function. Okay, so again third way, if I break this one also, then also I will get the same transfer function, right? So I will copy the transfer function and write them in front. Okay, the transfer function for all of these three cases, right, cases will be same only. So this one will be same. Okay, this one, okay, will be same. This one also will be same. Okay, so like with superposition you can also understand, right? This one will be zeros and this one will be same. This anyways not connected. Okay, but we are anyways taking the extra state variable. That is a waste now. That is a waste. So if MSQ comes, you mark uncontrollable, unobservable, both uncontrollable and unobservable. But if MCQ comes and you have no other option, generally that question should come as empty, right? That question should come as empty. But if you have no other option, then it should be both uncontrollable and unobservable. Okay, that is the last option that you have, right? You mark that, but you do understand, right? It can be anything, right? It can be anything. We can't say until and unless we know the state space representation. So this was that question. Now let's come to this question. For check for state controllability and observability of the system for state space representation. So again, we have been given a state space representation, and this time, right, we have a Jordan matrix basically. So this time, right, what I will do, I will solve this using the state diagram and also the what do you say, Gilbert's test. But the homework for you is you solve it using the Kalman's test. So I'm not solving using the Kalman's test because that will just take much time. Okay, so yeah, in the next lecture, right, I will solve you with the Kalman's test. Okay, so yeah, now, right, let me draw the state diagram for this one. Okay, let me draw the state diagram for this one. So how will I draw the state diagram for this one? What I see is this first state variable isn't connected with the input, right? So first state variable isn't connected with the input, but it is connected with the second state variable itself. It is connected with the second state variable. So let me draw this, then I think you will be able to understand. So this is, let's say this is my first state variable. This is x1 of dot of t, and this is connected with the output because here we have 1. Okay, connected with the output but isn't connected with the input. So we'll leave the input as it is, and we have like transfer function as -2, right? So x1 itself is coming back, so this will be -2 here, and also x2 is coming, right? So x2 is coming, so it will be something like this. x2 is something like this. This is 1 by s. Okay, this is 1 by s, this is 1. Okay, this is 1 by s, and this is x2. Okay, and this is again 1 by s, and again, right, we have a -2 coming from x2 itself. This is x2 dot. Okay, we have x2 coming back to x2 dot with -2. So I hope you are understanding. Now x2, right, x2 is connected with the input, right, with 4. x2 dot is connected with the input with 4, right? So here I will put the input, so I can bring this output down a bit. This is 1, and this is the input basically. So u is here, and this is the input. Okay, one of the input is connected over here. Okay, I should not connect this directly. What I should do is make a break over here, and this one, this is 4 actually, right? 4, and this is 1 only. So this is my input. Okay, one of the input basically, and then I have a third state variable that is just alone by itself, and it is connected to both input and the output, right? So like I can already see that this system is not controllable or observable, right? Or is it? Let's check, right? So where am I? So I will just draw the state space, and from the state space you see the diagram. Okay, then you tell me, is it observable or controllable, or it is not observable or controllable. So again, I have this one. This is x3, third state variable, x3 dot. Okay, and what is this? This is like -3, so like -3 will come over here. I hope you understanding that the drawing, right? So we have done this multiple times previously, so I'm not explaining anything right now, I'm just drawing it. Okay, so this is -3, then what is happening again, right? This isn't connected, this is connected to the input and the output also. So the input it is connected, and the output also it is connected. This is 1, and this is also 1, and this is this is 1 by, sorry, this is 1 plus. So yeah, this is basically this. So now tell me, by seeing the state space diagram, are they controllable or not? So yeah, this is not directly connected to input, and this is not directly connected to output. So my answer will be uncontrollable and unobservable. So if you said so, you are wrong, right? You're wrong. Why? Because basically, right, it is not directly connected to the input, but is there any forward path? So if I go from, okay, I forgot to write here, this is arrow also, here I have one arrow also, sorry. Okay, so here, right, if you notice, my u can travel from here to here, right? It can reach my state variable, right? It can reach my state variable, as my x2 is a function of u and x1 dot is a function of x2 itself. So x1 dot can also be controlled by u. Okay, so yeah, it is not directly connected, but still it is connected somehow, right? So but other state variables, it is anyway directly connected, so this system is controllable. Okay, and what about observability? So this is my y of s and this is my u of s, right? So what about observability? So observability, right, if my state variables are observable to it, right? So I can come from here, yes, I am directly connected to the output, and I can come from where, yes, I am directly connected to the output. So is this state variable, can I reach to y? If I go from here and here, yes, I can reach to y. Even though it is not directly connected, I can still reach out to y, right? Hence my system will be both observable and controllable. Okay, my system is okay. Let me write state space representation is both observable and controllable, right? It is both observable and controllable. Okay, so now check using the Gilbert's test. So let me copy the matrices. This one was the method 1 basically, but Gilbert's test is much more simpler. Okay, you don't need to do all this. So what does Gilbert's test say us? So let me copy all of this. Kalman's is again homework for you. Okay, so these are the matrices, so let me delete these. Okay, u this is deleted, this is a, this is b. Okay, what has came up? And this is c basically. Okay, put this here, this is c. So what I can see, what does the Gilbert's test say? So this is the method 2 basically. Okay, what is happening? Why is this coming up? I don't understand. So what does the Gilbert's test say? Please revise. So it says Gilbert's test basically, what does it say? It says that the row corresponding to the last row of the Jordan block, we have two Jordan blocks, and repeated Jordan blocks we don't have, right, for the same eigenvalue. So hence the first rule is satisfied for both of them, controllability and observability. Now the second rule, what is the second rule? Second rule is for controllability, this last row corresponding to the Jordan block should be non-zero, hence non-zero, that is okay. And this is also row corresponding to the Jordan block should be non-zero, so this is also okay. This is also okay, right? And what is the C matrix basically? Again, right? Okay, C I deleted the actual matrix, but the other things are remaining. Okay, C was 101. Okay, 101. For C matrix, the first column corresponding to the Jordan block should be non-zero. Yes, this is non-zero, and this is also the first column basically of the Jordan block, so this is also non-zero. Hence again, right, these are the same thing only. So I should write this like bottom, and I should change the arrow, make the arrow like this one. This is also non-zero, right? this is also non-zero. Okay, both of them are non-zero, right? Both of them are non-zero. So again, hence my system is both controllable and observable. From this we can see hence my system is both controllable and observable. Okay, so yeah, this is the end of this lecture basically. Okay, so what did we do in this lecture? Basically we learned about the Kalman's test. Okay, basically the definition and like the understanding. Then we did the Gilbert's test for both non-repeated and repeated eigenvalues. Okay, and then we solved few questions with the help of Gilbert's test. Okay, and this all these are method 3. This is the method 2. Okay, let me change the color of this one. This is the method 2 basically. And what is the method 3? The method 3 is basically Kalman's test. So that is homework for you again. So in the next lesson, right, we'll do again few things about the this last controllability and observability. Okay, last few things, 2 topics are remaining. Okay, those 2 topics we'll do. That's a very short thing, and then we'll directly jump to questions, right? Yeah, that is it for this lecture basically. Thank you for watching.